Okay, I just noticed here that I was duplicating the unit A while I should have used unit B and unit C instead. So I'm just adding the unit B, unit C, and unit D. So now we should have the right pinout on all of them. Okay. I realized also that I need to add more analog inputs, because these inputs are going to be used for both joysticks, both passive joysticks and active joysticks, and also for eventual position sensing of linear actuators, because linear actuators use potentiometers to sense their position, and at least the ones that I've seen, and it needs to be possible to attach both joysticks and the sensors at the same time. So I'm going to add 4 more analog inputs, which are going to support 5 volts, and they're going to support, just like these ones, both passive and active control on the input. Let's see. So duplicate block, and this is going to be, let's see, I want to align all of them. I'm going to align them by, let's see if the same function works. Yes, by pressing space you can see down at the bottom of the screen that dx, dy and distance have been reset. So now I can just move it to the side and make sure that dy is 0. Okay. I've noted down the regulators that I'm probably going to be using for the power supply. I'm going to need to have one that converts the 48 volts to 12 volts, which is also going to be output on a connector going to this drive. So that's why I'm not using the built-in buck converter in the motor control circuit here, because this one outputs 5 volts. And I need to output 12 volts on the side, so I have to use a dedicated buck converter for converting the 48 volts to 12, and then I'm going to have another one converting 12 volts to 5 volts, and then I'm going to have LDOs like this one converting 5 volts to 3.3 volts at low currents here. So let's see. Unfortunately, in KiCad it seems to be impossible to edit the graphics. So you have to like delete the graphic line and then put a new graphic line. It would have been nice if the graphic line was editable, just like normal polygon lines, or for example, so that I could just click and select drag polygon edge, but it doesn't seem to be possible. Okay, so we got quite a few of these. This is gonna take a lot of space on the PCB, but I think they're all gonna be quite useful. Okay, I've also, since the last video, I've also added the resistors on the input here, and these are good to have because there is protection circuitry inside the op-amp that will that can be damaged if there is too much current coming in at higher voltage. So I use 1K resistors here, just to, or 10K actually here in this case, to just make sure that the input voltage here is, let's see, yeah, and this one is not going to be mounted, right? Yes, so just to make sure that the input current here is limited. So let's see, and we got all the 5 volts connected to our power management controller here. I use the same chips as USB connections. Like USB sockets use these chips to enable power to USB devices. they have built-in current limit. Let's see. And this was a bit unfortunate that designators and IC names got reset to default. I'm going to edit this component actually. Right. I wonder if I can go to a library editor and this should be placing the fields in the right position. Okay. What if I reset this to default? Okay. How to place fields. Okay. So apparently for some reason it thinks that like out of place in the fields means putting them there. Could this be okay? What about unit B? Yeah, unit B, C, all of them the same. Okay. Let's update fields. No? Okay. Apparently it thinks that the fields fare better if they're placed completely outside of the symbol. For some reason. I don't know what the logic about this is. I don't know the logic that KiCad uses to place the fields, where it places them. It just seems weird to me. Okay. Hopefully the placement is not going to be reset for some reason later when I do some kind of update. When I update the fields, it doesn't reset the positions anymore, which is very nice. Before it used to do that, and that was very annoying. Let's see. Yeah. Okay, I'm gonna leave it there. Well, this one is a bit off center there. Okay, I'm not gonna be perfectionist about this anymore. Okay. So we got our analog inputs, and I also need to put analog outputs. And the way that, so I want to be able to generate potentiometer output, because that is sometimes necessary if there is any other control circuitry that is placed downstream which accepts an analog signal. It is very useful to be able to output potentiometer, to have kind of like a virtual potentiometer connection, so that the voltage comes from the other device and goes into the potentiometer on my board, and then outputs an analog voltage which is between the VDD and ground supplied by the other device. And the way I'm going to solve that is by adding a digital potentiometer. But I think at this point, I think I'm going to wait before I add the digital potentiometer, because I want to add the other important inputs first, like digital inputs and digital outputs, and then see if it will make any sense. Now, this needs to be also updated, so I'm going to update the labels as well. Part 4, let's see, so this is, okay. So it seems that I haven't updated this labels. Let's see, have I forgotten anything else here? The artifacts of copy pasting. So let's see. And even if I had this in a sub-circuit or sub-sheet, it still wouldn't solve the issue. I still have to duplicate the sub-sheets and then label the outgoing labels appropriately. So this is just something that one has to be pay attention to. 4, 5, 5, 6, 7, 8. Okay, what can we do next here? Maybe it is time to put together the power supplies. Although that would be a subject for a video on its own. Let's see if there's anything else we can do with analog. Right, I'm gonna update this. Let's see. I have to unlock this. Is control L? Yes. For some reason all of my boxes got locked, so I have to press Control L to unlock them. I don't know if there is any shortcut that locks everything. Shall we have 4 analog outs? I think we should. Yeah, let's just have 4 analog outs, and we can have 8 analog in. Let's see. So I think we can replace this. We can actually replace this with individual boxes. This is locked as well. Let's see. So this is going to be 8 analog in. And then it's going to be let's see, 2x PVM in, and how many digital IOs do we need? And we need 8x digital. So digital IO. When it comes to placing digital IOs on boards like this, one has to consider the fact that it's very easy to do something stupid and just connect some high voltage to the digital input pin. So it's very important that as many connections as possible can tolerate high voltages. So this is going to be either digital in or digital IO. For now, I think I'm going to make it digital in, because inputs are more important here. We need to connect buttons to this board. So, so the analog inputs can be used for analog control or for connecting joysticks directly and controlling different parameters. Basically, just interacting with the board. And then we also have 2 PWM inputs, for one for each motor, to control speed or torque using PWM. We don't need PPM, so I had an idea that I would put PPM here, but I think PWM is enough for this case because we only have two channels. So if I don't have enough pins for connecting 2 PWM signals, then I may consider using PPM instead. So then I can have both commands in one wire. So I would just transfer the command for one motor after the other. But for now, it's going to be two times PWM in. Brake input is going to have to be a separate input that goes directly to the brake. Let's see. This would be. This is locked. Let's just make this a three pin plug. This would actually be a 2-pin plug. So it's going to be a connector and ground. Or actually, either that or one 3-pin plug. I'll have a think about that. I have to save space on the board as well. The digital inputs are primarily for buttons, so this can be also used to set direction. So we can remove direction and just make this. Let's see, 2-pin plugs, and then there is fault control. So fault is an output. Fault can be a good thing to have. So this would be part of digital outs. So how many digital outs? I'm not sure yet. Or actually, yeah, so if we have 8 digital inputs, we should also have 8 digital outputs, at least for the sake of having the possibility to control backlighting on things like buttons. But in this case, I don't know if 8 would be even enough. I think we should have another one for fault. So if we connect buttons here and the buttons have backlights, then having the 8 digital outs is good, and be able to use them together with the inputs. So it would be essentially a 3-pin plug as well. This is going to be a lot of plugs. This seems to be, yeah, this is probably going to have to go on there on its own connector. Actually, I'm gonna maybe I'm gonna need to use a pin header into which one of these flat cables connect. I'll see. Okay, and I also added LCD interface, so that's more pins. That's gonna take even more pins on the microcontroller. It may very well be that I will have to sacrifice something in this block diagram. It may be that everything wouldn't actually fit, but we'll see. One plan B would be to use I2C parallel ports for digital inputs and outputs. That's one way of doing that. They're not going to be fast, but they're going to do the job. Okay. So we have analog in and analog out. Let's move this. I have to make this fit into a rather manageable size. I don't want to have a board that just has connectors upon connectors. It has to be space efficient. Okay, so for the analog out, I will use a chip that simulates a potentiometer. Let's see here. These chips are called digital potentiometers. digital IC potentiometer. And the chip I'm looking for should save the potentiometer value. It should be non-volatile. So I'll look for I2C. Actually, maybe SPI is better. SPI is more reliable in this case. I think SPI is much better. Let's see. Two-wire parallel. Okay. Let's see what we get here. Okay. So 24 alternatives that have SPI. And I also need the quad. I want to have 4 of them. Non-volatile. And I don't get quad potentiometers in non-volatile. Okay, they're not supposed to be that expensive. I don't want to use something that's that expensive. This one is SPI dual. Okay, maybe I need to sacrifice the type of interface that I'm going to use. Let's see. Let's use quad 256 non-volatile. 76 left. Yeah. Okay. It would be nice that if the potentiometer pins can support 6 volts or more. Yeah, they definitely need to support 6 volts because the input can very well be 5 volts. In fact, will usually be 5 volts. But these things are expensive. They are quite expensive. Okay. I mean, for a potentiometer. Let's find something cheaper. Okay. AD5143 seems like something. Okay, maybe we can sacrifice a number of steps. Let's see what we can get here. Yeah, this definitely makes a difference. So with 129 steps, we pay almost 4 times less. Okay. MCP 4442. Okay. MCP 4442. 1000, yeah, 50k. Okay, this one is 100k. 100k is too much. What is the maximum voltage? So let's see. To 5.5 volts, which is nice. Okay. So there is quite a few alternatives, and I will probably use the TS SOP, and it's gonna be 10k. So 10K, 4461. Oh, that's nice. 257. Let's have a look at this one. I'm curious to see what voltages it supports on the potentiometer pins. Okay. Yeah, this is the one we're going to use. Okay. Quite possible that it's 5.5 volts. Okay. Right. Okay. So VDD plus 0.3 volts. And VDD can go up to 7 volts. So 7.3 volts is the maximum on these pins. So this is going to be a 5 volt interface. And it's quite a long data sheet. There is a lot to learn about digital potentiometers and their intricacies and their secrets. Okay. I'm not 100% sold on that one though. But I think that's probably the one that I'm going to be using anyway. Because then we get into the price range of 5.7 euros per chip. And to me that's a bit too much to pay for a potentiometer. Okay, so the difference between a potentiometer output and a digital to analog converter is that potentiometer actually works like a resistor. A digital to analog converter works more like an op-amp, so it outputs a low impedance. It has a low output impedance, the DAC, while the potentiometer just works like a resistor divider where you can adjust the resistances. For this application, what I'm looking for is a virtual potentiometer. Not many motor drives out there that have potentiometer outputs. Okay. So which one was it that I was looking at? I think it was the one that had 257 taps. I think it was this one. Let's see. MCP 44. 4462. This seems like... Oh, no. No. Not 4462. If I were to choose the 4462, I would end up with this thing. Let's see here. I would end up with this shit. 4462. Which just provides two pins. So I need 4461. So this one. 10K, 1200 in stock. Let's add it to the library. Okay, this is going to be a completely new symbol because I think we're going to need to draw a few things here. So adding a new symbol, and then adding the manufacturer number, and then I'll just make sure that the manufacturer number does not show up. And then I will move this out of the way. Okay. Is there a possibility to use, let's see, potentiometer. Potentiometer. Let's see. It would be nice to reuse the graphic. To hell with it. It's gonna be too big anyway. So I'm gonna go back. Let's see. SP44. Yeah, no, there we go. 61. I'm just gonna draw the symbol from scratch. And look at this diagram here. So let's see. I'm gonna add the pin first, all the pins first. So P3A is 1, and it's a passive. I'm gonna have to read also the data sheet and just make sure that this chip does exactly what I want. P3 wiper is 2, passive as well. Let's see, P3B 3 A0. So that would be the I2C address. And what does HVC do? I'll find out later. HVC A0. That will be an input. That will be input. And SCL, SDA. Pin number 5 and bidirectional. And SDA, pin number 6, bidirectional as well. Or rather, SCL is actually an input because it's only going one way. Let's see. VSS and VDD. So this would be GMD. Power input. I've kind of come to the conclusion that anything that is not a power output is always a power input, even if it's ground. Let's see, P1B is 8, which would be a passive pin, and P1 wiper is 9, also passive. And P1B 10, also passive. Wait, A, yes, P1A. Okay. Going to the left, P0A, pin 11, passive. Place it here. P0 wiper, pin 12, passive. And P0B, pin 13, passive. And then we have write protect, reset. So write protect is pin 15, reset pin 15. No, pin 15. And next is A1, pin 16, which is then all of these are inputs. Reset also an input. Write protect also an input. And my dog just found a ball. Soon I'm gonna get the ball on my lap and she's gonna want me to play with the ball. Okay, VDD pin 17 power input. And P2B 18. Oh my god, soon things are gonna be falling. Because now the ball has rolled somewhere where she cannot easily get it out. Let's see. P2W. Passive. 19. Oh, okay. I just got distracted. So pin 18 is P2B. Let's see. So this would be 18. Passive. And pin 19 is P2W. Pin 19. Passive as well. And then we have pin 20. P2A. Pin 20. Passive. Good. Okay. Cool. Now just draw the outline and finally move this to the center. Oh no. Okay, so I'm gonna move this a little bit just to get a little bit more symmetry. Let's see, drag rectangle edge. I want to drag this rectangle edge. Drag rectangle edge. Yeah, like that. It's better. Okay, and finally I'm gonna assign the footprint. And this is, I think, this is TS-SOP 20. Alright. But what is the actual size of this? Let's see. So, fine. TS-SOP. TS-SOP. I want to find out the width of this package, because width of TS-SOP packages can vary, and you never know exactly which one they use unless they specify it. So, and TS-SOP does not have exposed pad, which is good. What is right dimensions? There we go. 20 pin is 660, 640. So in the footprint, I'm really gonna have to get that ball soon. Okay, in the footprint, TS-SOP. Let's see. Where? Let's see. I think it's here. Yeah, HT-SOP, and then there is TS-SOP. TS-SOP 20. Although this one is 6.5 and pitch 0.65. 4.4, 6.5. This is not really the dimensions that I get here. Let's see. Can they not just show exact dimensions of the package? Oh, there we go. There we go. So, where is the E? Okay. Yeah. So we're interested in D or E1, I think it's E1 that KiCad specifies. So it's 440, which is 440 and 65 for D. So D is, oh, D is 5. Okay. Oh, this is the smaller one. I think this is probably for the smaller one. Could it be for the smaller one? Yes. Okay, let's see. Let's see if there is the big one somewhere. I think this is the right footprint. I just want to make sure. I don't want to be in a position where I have a board with wrong footprint. Really annoying. So 650, yeah. This seems to be right. And the pitch, just to make sure the pitch is a small e, which is 0.65. Yes. Good. Okay. Oh, I just forgot something. I just forgot to name my IC with an IC prefix. So, let's see. M. Where is M? There we go. IC. Okay. Four. Okay. I'm gonna go ahead and actually pause this video for now and go play with my dog a bit, and I'm gonna come back to this video and I'm gonna continue laying out the analog outputs.